Hey guys, welcome to Crown Maths. In this video, we want to discuss still on algebra, but a nice proposition which says let this arbitrary sequence be a family of algebra of subsets of R. Then the arbitrary intersection is an algebra. So we want to show that given a family, an arbitrary family of algebras, then the arbitrary intersection we give is still what? An algebra. So for us to show that this arbitrary intersection forms an is still an algebra, we have to show that the empty set, okay, is in the algebra, is in this intersection. We have to show that given any two sets coming from this intersection, then the arbitrary union, no, not the arbitrary union, their finite union is in this arbitrary intersection. And also if a set is coming from here, then its complement is also what? In this arbitrary intersection. So okay, let's prove it. Now before we start, I need you to understand something. Whenever we say, this is just aside, okay, whenever we say A intersects B, okay, A intersect B means the common element between the set A and the what? Set B. So that common element, that means find that common element between in both these two sets. So if I say X is in A intersect B, so this implies that X is in A and X is in what? B, because X is a common element in A and what? B. So I just want to use this idea here to work on this proof, okay, on this proposition I mean. So now let's start. Now I said for us to show that this is an algebra, I have to show that it satisfies the what? The three conditions. So for the first one, for the first part, now observe that from what we say let this be what? An algebra. So since for every alpha in the index set, since for every alpha in the index set, this this our fancy A is an algebra, okay, since for every alpha in the indices this our fancy A is an algebra, then this implies that the empty set is in what? In the algebra for every alpha in what? In the index set. Okay, so what it means is that since for every alpha, remember, since for every alpha, that means for every alpha I pick here, this is an algebra, then it means that since it is an algebra, definitely the empty set must be inside it, right? So the empty set is already inside it for every alpha I pick. So, and also now if empty set is in the algebra for every alpha you pick, what does this imply? That means empty set is in all the algebra. So this implies that the empty set is an element in the arbitrary intersection of what? The algebra. Okay, so I've shown that the empty set is in the what? Algebra. Now the second one, now we're going to pick an element in this and show that that element is inside its complement, sorry, it's inside that algebra. So we say take any A in the arbitrary intersection alpha in this. So we take any A in this, okay. Now if we take any A, what does this imply? This implies that for any alpha in the intersect, that A is in A alpha. Okay, now this is as a result of what? Intersection. Remember, this is intersection of algebra. So when we pick any A in the intersection of the families of algebra, that is, you're having families of algebra. Let me give an example. Let me just space something like this. We have the fancy A1, fancy A2, fancy A3, and so on. So when you do the intersection of these fancy A's, okay, so when you now pick a set or an element in the intersection of this fancy A, is the same thing as saying A in what is in A is in all those what fancy A's. And this is happening for every alpha in the what index set, right? So once A is coming from the intersection, meaning that A is in this alpha for every alpha you pick. That is, for every alpha. If alpha is 1, A is here. If alpha is 2, A is here. If alpha is 3, A is here. Okay, so since A is in this, what does this imply? This implies that A complement is in what? Is in this for every alpha in what? Index set. And why is this so? Since this is an what? An algebra. An algebra. Okay, now the A complement is in this because it is what? An algebra. So if A is in the algebra, is an element in the algebra, then its complement must be in what? In the algebra. Okay, so now if its complement is in the algebra for every alpha you pick, okay, that means A complement is in all the algebra, the family of algebra, then this implies that A complement is in the what? It's in the arbitrary intersection of what? Those algebras. So we have shown that if we pick an element in this intersection, its complement is also in the intersection, so it satisfies the second condition, right? Now we want to show for the third condition. Now we are going to pick any two sets in this intersection and show that its finite union is also in this what? Intersection. So take any A, B in this arbitrary intersection of algebra. Okay, now if we take any AB in the arbitrary intersection of algebra, this implies that for every alpha in the index set, AB is in what? Is in the algebra. So since it's an intersection, it means that A is in all of them, right? For every alpha what you pick, A and B are in all of them. Okay, they are common elements in their what? In this intersection. So now what happens next is, since A and B are inside the algebra, so this implies that for every alpha you pick, that A union B is in what? Is in the algebra by the third property. If A and B are in the algebra, then their finite union is in the what? Algebra. Okay, so this is since this is an algebra. Okay, now, and of course, but we're not done yet. Now remember, since the finite union is in the algebra, okay, and this is happening for every alpha in the index set, then this implies that A union B is in the arbitrary what? Intersection. Is in their intersection. Okay, so this implies that this is in the intersection. What this means is that now, since, do you remember the union is like saying just one set? The union of A union B is like saying, okay, A union B could be C, okay, a set C. Now let's say that this union is in this for every alpha I pick. So for every alpha I pick, as for every algebra in the family of that algebra, now if this is common in all of them, what this means is that then this is in their intersection. Okay, so we have shown that it satisfies the three conditions. First, we've shown that the empty set is inside it. We show that if we pick any A in this, its complement is here. And lastly, we've shown that if we pick any two sets in this intersection, then their union is also here. So what this means, hence we have shown that this is an algebra. Hence, this arbitrary intersection of the family of this is an what? An algebra. Okay, so we have finally shown that this arbitrary intersection of algebra is an algebra. Okay, remember here was arbitrary intersection. So sometimes they might give you to show that given two algebra, show that the intersection of these two algebra is an algebra. So showing that this arbitrary intersection is an algebra is like an extension of showing that, okay, a finite intersection of algebra is also what? An algebra. So it might be two algebra, it might be three algebra given, and they ask you to show that the intersection is an algebra. So showing this has already shown those ones. Okay, so now I want to ask a question. Does union of algebra form an algebra? Well, the answer to this question is no. The union of algebra may not necessarily form an algebra. Okay, so let me remember to show that the union may not necessarily form an algebra, we need to find a case. It is sufficient enough to find an example that contradicts it. Okay, that satisfies the fact that it does not what shows that that their union does not form what an algebra. So but in generally, the union of algebras, okay, does not what form what an algebra. Okay, so let's consider an example. So consider the following classes of subset of R. So let's say consider the following classes of subsets of R. Okay, so the first algebra, let's form an algebra here, the empty, the whole set. Okay, to now the complement. Remember, the empty, the complement of it is R. Okay, so this is the first algebra. Now this is the second algebra, the empty, the real, singleton 6, R without the singleton 6. So this is another algebra. Now let's form their union. Let's see what we have. One union. Okay, what would this give me? The empty, the R. If you do their union, this will come in, 6 will come in, then R without 2 will come in, R without 6 will come in. Okay, now look at this very well. Now we are considering the following subsets of R. Now this is an algebra, this is an algebra, but let's see if their union is an algebra. Now observe that when we did their union, when we did this union, we got this, right? Now if you look closely, you discover that this is not an algebra. Do you know why? If I should pick the singleton 2, if I pick an element in this algebra, now this union has formed an algebra. If I pick this in union, if I pick this singleton from this algebra, and I pick also this, okay, from this algebra too, okay, if I pick these two elements from this algebra, their union, what is their union? Their finite union is what? 2, 6, right? But is 2, 6 in this algebra? No. So definitely it's the union
or the arbitrary union, whether arbitrary or not, does not necessarily what form what an algebra. So this is an example to show that this does not what form an algebra. Thank you for watching this video. Please do not forget to like and subscribe, and also share to your friends. Thank you.